Hello again. Hi again, I hope everyone is well. So this is the homework on section 4.3, and as I mentioned before, what I'm going to do is I'm just going to do a selection as though we were in class and someone had raised their hand and said, could you do this one from the homework? So I'm in section 4.3. I'm on page 296 in the book, and if you don't have a copy of the book open, then probably you should pause this video and do that. Open a copy of the book so that when I'm reading the question, you have it right there in front of you. Sometimes, in particular, the question asks you to look at a graph or something, and you're really kind of without a clue unless you have the book open in front of you. Okay, so again, page 296, section 4.3. The first question is Scale Builder 1, so I'll read it, but you should have it open in front of you. It says, two p-values are given. Which one provides the strongest evidence against H0? So again, this is the hypothesis test arguments are not the kind of arguments that a person makes in everyday life. They take a little getting used to. So there are two people, the H0 people, the people in the seats at that holiday in Kansas City, and the HA person, I imagine it to be a doctor standing on the front of the stage at that holiday in Kansas City. There are two people having an argument. That's not pottery throwing, that's reasoned discussion. The people in the seats are maintaining that the true value, the census value, the population parameter is the nominal value, and the person in front of the room says, no, you need to change your mind about that. So always these arguments go that the person in the front of the room says to the people in the seats, you need to change your mind, and the people in the seats say, okay, you're going to have to convince us. The way that it works is the person in the front of the room has to say to the people in the seats, suppose you're right. Suppose you're right, then here's what samples would look like, and they provide a sampling distribution like we've been doing, in our case using StatKey. And here's what samples would look like. And the sample I got is so way off, is so rare, that it's hard to believe you could be right. So again, you imagine that we're testing somebody. You say to me, my friend is a really good coin flipper, and I say I really kind of doubt that. So you go get your friend. Your friend comes in the room. I am H0. I'm asserting that your friend has got a p equals 0.50, just like everyone else in the world. You're asserting that your friend has a p greater than 0.5. You're asserting there's something interesting happening here. I'm asserting the nominal value. So, of course, we need data to support this argument. So the person flips a coin 100 times, and they produce a p hat. Now, if your friend's p hat is 0.53, that is, they got 53 out of 100, I'll say, it's just not, you're going to have to do better than that. That's just a sample thing. If, on the other hand, your friend gets a p hat of 0.89, 89 out of 100 flips, well, that's such a way off sample compared to what I expected that I guess I have to change my mind. Okay, so what convinces the people in the seats is when the sample would be rare. That is, the HA person says, suppose you're right, and produces the sampling distribution that I think samples would suit, that the H0 people think samples would fall. And then the HA person says, let's look at my sample. It's so rare that it's hard to believe you could be right. Which is easier to believe, that you're wrong or that my sample is an incredibly rare once-in-a-lifetime event? And of course, in that context, reasonable people say, well, I guess I must have been mistaken. Okay, so unlike in regular everyday life, what convinces the people in seats is a low probability. What convinces the H0 people to change their mind is when the p-value is small. Is that when the sample, in this case p hat, sometimes it's x bar, when the sample is so far out there on the sampling distribution, the p-value is small, and we say, well, I guess what I proposed for the sampling distribution was just simply not right. Okay, so here, reading the question again, two p-values are given. Which provides the strongest evidence against H0? The H0, you never argue in favor of H0. You always argue against H0, and you try to come up with strong evidence against H0. What strong evidence against H0 is when the p-value is small, when the sample had only a very small chance of happening in that context. When your friend came in the room, flipped a coin 100 times, and got 89 heads, and we would say, well, that can't just be just chance. Okay, so 4.80 says a p-value of 0.9 or a p-value of 0.08. So the p-value of 0.08 is small, so it provides strong evidence that the H0 people are mistaken. 82, I'm only doing the evens because the odds answer in the back of the book so a person can try themselves and see if they understand. 82 says a p-value of 0.007 versus a p-value of 0.13. So again, I picked the smaller of those two, 007, provides stronger evidence that H0 needs to change their mind. So a small p-value, not like in everyday life where you hope for large probabilities, a small p-value convinces H0 to change their mind. So a small p-value is what HA is hoping for. Okay, so Scale Builder 2. It says in these exercises you get a p-value, state the conclusion of the test based on this p-value in terms of reject H0 or fail to reject H0 if we use alpha equals 0.05, a 5% significance level. Okay, so I'm going to do the two even ones. P-value of 0.0007. Now 0.0007 is much less than 0.05, much less than a 5% chance. So that convinces the H0 people to change their mind. The technical jargon is you say reject H0. 4.86 says a p-value of 0.2531. So 2531 is not less than 0.05, not less than a 5% chance. It's in fact an everyday possibility. 25% chance of something happening. It happens all the time. So the H0 people will say, you failed to convince me. You're going to have to do better than that. We failed to reject H0 or do not reject H0 or whatever way you want to phrase it. Okay. Scale Builder 3, it says use the p-value given and they ask are the results significant at 10%, at 5%, or at 1%. And again, I'm only going to do the even ones. So for this one, I thought maybe a piece of paper. So the p-value is, the p-value is 0.0320. So p-value 0.0320. So that's about a 3% chance. So is that significance at the 10% level? Is it significant at the 5% level? And is it significant at the 1% level? So 3.2% is indeed less than 10%. So if that's your criteria, then the null hypothesis people would change their mind and say, okay, we reject the null hypothesis. 3.20 is less than 5%. So again, yes. 3.20 is not less than 1%. So this number is not less than 1%. So the H0 people say, I'm sorry, my criteria is very strict. You're going to have to do better than that. The other even numbered one here is 0.008. Now that's not 8%, that's 0.8%. So that's less than 10%, so yes. That's less than 5%, so yes. And it's also less than 1%, only just barely, but just barely is just barely, so yes there also. So in all those cases, we reject H0. All those cases, we reject H0. Okay, one more I wanted to do here, the question number 97. I know that it's an odd number, but I wanted to go over that one. It says data 4.3 on page 265 discusses a test to determine the mean level of arsenic in chicken meat is above 80 parts per billion. So we're arguing about the number 80. So H0, it says in the question, is mu equals 80. We're arguing about whether the number is bigger than 80. So mu equals 80 is H0, that's the nominal value, and HA is mu is greater than 80. So that's exactly expresses in formulas, and I know formulas, and not everybody in the room thinks first in formulas, but that a person can see when it's pointed out to them that 80 and greater than 80 is exactly what the argument is about. Okay, then it says if the restaurant finds significant evidence that the mean arsenic level is above 80, then they'll stop using that supplier. So samples from two different suppliers are analyzed. The resulting p-values are given. Sample from supplier A is that the p-value is 0.0003. 0.0003. And then sample from supplier B is 0.3500. So supplier A is a p-value of 0.0003, and supplier B is a p-value of, let's see, it's 0.35, 0.3500. Okay, the questions. Interpret each p-value in terms of the probability of the result happening by random chance. So I'll start with this one here because a person recognizes that 35%, so it's easier to say out loud. 35%. So the null hypothesis people believe that mu is 80, that if you didn't sample just a dozen chickens, if you sampled thousands of chickens, you'd come up with you'd know the real number, and the real number would be 80. In this context, what we got is a sample, an X bar, that shows a p-value of 0.35. So the null hypothesis people draw their sampling distribution, and they get it centered around 80. And our particular sample came out as being something that had about a 35% chance of happening. Our particular sample, whatever it was, X bar in there, came out as something with about a 35% chance of happening. So in this context, the null hypothesis people say 35% chance of happening is an everyday chance of happening. You're going to have to do better than that to convince me that you've not provided strong evidence that the number really is above 80. This could easily be just a sampling thing. On the other hand, the p-value of 0.0003, it's the exact same picture. The distribution of samples is centered around 80. And this time, the X bar is way out there, so that the percentage of this curve, that is the percentage of dots that are colored by stat key, would be very small, in tiny percent. And you'd say to yourself, I just can't believe that by some freakish chance we got a sample way out. I think there must be something for real there. It can't be freakish chance. It must be for real. It says, interpret each p-value in terms of the probability of the result happening by random chance. So, in this case, the X bar is on a place on the curve where the chance of an X bar happening by random chance, by just happenstance, is 35%, X bar or further out. Same thing here is that the chance of X bar or further out is not 3%, not 3/10, but 3/100 of 1%, tiny chance. Part B, which p-value shows stronger evidence for the alternative hypothesis? Which p-value shows strong evidence that the chickens really are full of arsenic? So here, this could happen. This could be a sampling thing. This could happen by random chance. Here, come on, there's no way. This isn't random chance. This is arsenic-filled chickens, is what we're looking at here. And then C, which supplier should the chain get the chickens from in order to avoid arsenic? So clearly, you're going with B here. Clearly, you're getting rid of A and you're going with B. Okay, very good. I hope I hope that a person, after seeing these videos, will try the questions that I have not done. Will not just watch the video and say, oh, okay, I understood everything that happened and I'm good. But instead, we'll try the odd-numbered ones and the questions that I have not yet asked, because that's the only way to make sure that you're understanding, what happened. It's only by coming to some point and saying, oh, I don't get it, what's happening? Oh, right, look at the video, that I remember now. And getting unstuck, that's the only way that you really learn the material. Okay, very good. And again, I hope everybody stays well, and I'll be back next week.